January 1943. The South Pacific. Lieutenant Commander Robert Morse stands in the charred hold of a cargo vessel at Nouméa harbor. The ship never saw combat. No torpedo struck her hull. No bomb fell from the sky. She burned from within. Morse is a U.S. Navy ordnance officer. He is here because ships keep exploding without explanation. The pattern emerged in late 1942. Ammunition carriers sailing from Pearl Harbor to forward bases began reporting fires in their cargo holds. Some crews contained the blazes. Others abandoned ship as magazines cooked off in cascading detonations. The losses mounted. 3 vessels gone in November, 2 more in December. Each one carried artillery shells, mortar rounds, and small arms ammunition needed by Marines fighting on Guadalcanal. Each one vanished not from enemy action, but from something inside. Morse receives orders in early January to investigate. He is 34 years old. Before the war, he worked as a chemical engineer for DuPont in Delaware. The Navy commissioned him in 1941 and assigned him to the Bureau of Ordnance. His specialty is explosive stability. Now he must discover why stable ammunition becomes unstable at sea. He begins at Pearl Harbor. The base ammunition depot stores shells in concrete bunkers with thick walls and controlled temperature. Workers load cargo ships at night when air is coolest. Standard procedure calls for wooden dunnage between ammunition pallets. The wood prevents metal-to-metal contact. Steel bulkheads separate different types of ordnance. Everything follows regulations written for Atlantic convoy operations. Morse boards the SS John Burke, a Liberty ship preparing for a Guadalcanal run. He descends into hold number 3. The space is 40 feet deep and 50 feet wide. Wooden pallets hold 500-pound bombs in neat rows. Dunnage timbers create a lattice between layers. The arrangement looks proper. He places his hand on a steel bulkhead. The metal is warm to the touch. Outside air temperature is 82 degrees Fahrenheit. Inside the hold it feels warmer. He requests a thermometer. A deck officer brings one from the bridge. Morse hangs it from a cargo net in the center of the hold. He waits 30 minutes. The mercury rises to 91 degrees. The ship is still in harbor. The sun has been up for 2 hours. He asks the deck officer about ventilation. The man explains that cargo holds have ventilation shafts, but crews often close them during loading to prevent rain damage. Once at sea, hatches stay sealed to maintain watertight integrity. The holds become closed boxes. Morse does calculations in his notebook. Steel absorbs heat. Wood insulates but also traps heat. In tropical waters under direct sun, a ship's steel hull can reach 140 degrees Fahrenheit. That heat radiates inward. A sealed hold becomes an oven. Ammunition has heat thresholds. Artillery propellant becomes unstable above 120 degrees. Some fuses activate at 135 degrees. The wooden dunnage itself can ignite. He travels to Guadalcanal in February. The forward supply base at Lunga Point receives ammunition daily. Morse inspects ships as they arrive. He finds holds registering 115 degrees. Some reach 125 degrees. Crews report smelling propellant vapor. That means shells are sweating out their chemical compounds. The ammunition is cooking. One ship arrives with scorch marks inside hold number 2. The crew contained a fire 3 days earlier. Morse examines the site. The burn pattern starts at the bottom of the stack where dunnage meets the hull. Heat conducted through steel, ignited wood, and spread to ammunition packaging. Only quick flooding of the hold prevented detonation. He interviews the ship's captain. The man is 50 years old and sailed merchant vessels for 20 years. He says the problem is new. Atlantic runs never had this issue. The captain explains that North Atlantic water temperature stays below 60 degrees even in summer. Cold water cools the hull. Pacific water at the equator runs 85 degrees. There is no cooling effect. The ship becomes a greenhouse. Morse sends his findings to the Bureau of Ordnance in Washington. His report states that current cargo procedures are incompatible with tropical operations. He recommends immediate changes. The Bureau responds in March. They want specific solutions, not just problem identification. He sets up a test facility at Nouméa. The Navy gives him a warehouse and a team of 6 enlisted men. He orders materials: aluminum sheeting, reflective insulation, thermometers, and ventilation fans. His goal is to redesign ammunition storage from the hull up. First problem: the steel hull. He cannot change the ship's structure. He can change what touches it. He designs a barrier system. Aluminum sheets go against the hull. Aluminum reflects heat rather than absorbing it. Between the aluminum and the cargo, he places a layer of asbestos insulation. The combination creates a thermal break. Second problem: the wooden dunnage. Wood is cheap and abundant, but it traps heat and burns. He replaces it with aluminum pallets. The metal conducts heat away from ammunition rather than holding it. The pallets have ventilation holes. Air can circulate through the stack. Third problem: sealed holds. He designs a forced ventilation system. Intake vents at the bottom of the hold draw cool air from below the waterline. Exhaust fans at the top expel hot air. The system creates continuous airflow even when hatches are closed. Fourth problem: monitoring. Crews need to know when holds are getting dangerous. He creates a temperature protocol. Thermometers go in 3 locations per hold: top, middle, and bottom. Crew checks them every 4 hours. If any reading exceeds 100 degrees, ventilation increases. If any reading exceeds 110 degrees, the ship diverts to the nearest port for cooling. He tests the system in April. A cargo ship receives the full modification: aluminum barriers, aluminum pallets, forced ventilation, and monitoring protocol. The ship loads 800 tons of ammunition and sails for Guadalcanal. Morse goes with her. The voyage takes 9 days. They cross the equator on day 4. Outside air temperature reaches 95 degrees. Sea temperature is 84 degrees. The sun beats on the steel deck. Morse checks the holds every 4 hours. Hold number 3, the deepest and hottest, reads 89 degrees at the bottom. Hold number 1 reads 85 degrees. Both are 30 degrees cooler than unmodified ships. The ventilation system works. Cool air enters from below, rises through the aluminum pallets, and exits through the top fans. The aluminum barriers prevent hull heat from reaching the cargo. The thermometers give early warning of any hot spots. They arrive at Guadalcanal with no fires, no vapor smells, and no overheating. The ammunition unloads in perfect condition. Morse has his proof. He returns to Nouméa and writes a detailed technical manual. The document is 47 pages long. It includes diagrams of the aluminum barrier system, specifications for the pallets, installation instructions for ventilation fans, and the temperature monitoring protocol. He submits it to the Bureau of Ordnance in May 1943. The Bureau approves the system in June. They designate it the Morse Thermal Management Protocol. Orders go to every Navy shipyard in the Pacific. All ammunition carriers must be modified before their next combat loading. The work begins immediately. Shipyards at Pearl Harbor, Nouméa, and Espiritu Santo install the systems. Each ship takes 3 days to modify. Welders attach aluminum barriers to hull interiors. Carpenters remove wooden dunnage. Metal workers install aluminum pallets. Electricians wire ventilation fans. Quartermasters receive thermometers and log books. By August 1943, 40 ships operate with the new system. By December, 120 ships. The modification becomes standard for all new construction. Liberty ships and Victory ships come out of American shipyards with Morse systems already installed. The results are immediate. Spontaneous ammunition fires drop to 0 among modified ships. Unmodified vessels still report incidents. In September, an unmodified cargo ship explodes at anchor in Purvis Bay. The blast kills 23 sailors and destroys 2 nearby vessels. Investigation shows the hold temperature reached 138 degrees before detonation. The ship had been scheduled for modification the following week. The incident accelerates the program. The Navy makes modification mandatory. Any ammunition carrier without the Morse system cannot load explosives. By March 1944, every ammunition ship in the Pacific Theater operates with thermal management. The system enables operations that were previously impossible. The Navy can now pre-position ammunition at forward bases without fear of spontaneous detonation. Ships can loiter in tropical anchorages waiting for invasion orders. The sustained bombardments that support amphibious landings depend on this capability. At Kwajalein in February 1944, ammunition ships stand offshore for 6 days, supplying continuous naval gunfire. At Saipan in June, they remain on station for 3 weeks. At Leyte Gulf in October, they support the largest amphibious operation in the Pacific. None experience thermal incidents. The Morse system makes it possible. Morse continues his work throughout 1944. He refines the ventilation design to reduce power consumption. He develops portable cooling units for smaller vessels. He trains Navy cargo officers in thermal management principles. His manual becomes required reading at the Naval Ordnance School. In January 1945, the Navy promotes him to commander. He receives the Legion of Merit for his technical contributions. The citation states that his work prevented the loss of at least 30 vessels and 2,000 lives. The actual number is likely higher. Many ships that would have exploded simply did not. There is no way to count disasters that never happened. The war ends in August 1945. The ammunition ships that supplied the final operations against Japan all carry Morse systems. The invasion of Okinawa required 180,000 tons of ammunition delivered over 3 months. Every ton traveled in thermally managed holds. Not one ship was lost to spontaneous detonation. Morse returns to civilian life in October 1945. He goes back to DuPont, but his work shifts. The company asks him to apply thermal management principles to industrial chemical storage. Explosives are not the only materials that become unstable with heat. He spends the next 20 years designing temperature control systems for chemical plants and refineries. The Navy keeps his system. Post-war ammunition ships retain the aluminum barriers, ventilated pallets, and monitoring protocols. The principles extend beyond ships. The Air Force adopts similar methods for tropical air bases. The Army uses them in desert ammunition depots. The basic insight that heat management is as important as physical security becomes doctrine. Morse dies in 1968 at age 59. His obituary in the Wilmington newspaper mentions his DuPont career and his Navy service. It does not mention the ships that did not explode or the sailors who came home, because cargo hold stayed cool. That knowledge lives in technical manuals and Navy archives. The last World War II-era ammunition ship retires from service in 1982. Workers dismantle her holds and find the aluminum barriers still in place, still reflecting heat after 40 years. The metal shows no corrosion. The design was that sound. Today, every military vessel that carries explosives uses descendants of the Morse system. The materials have changed. Modern composites replace aluminum, electronic sensors replace mercury thermometers, but the principle remains. Heat is a weapon. Managing it is survival. One engineer in a charred cargo hold understood that in January 1943, and his solution still protects ships at sea.